1 by Fs. 1 by
All right, so here, so when you solve for this is what it boils down to. V out is equal to D times V in, right? That's what it boils. That's the, and then you can say, okay, this is basically your transfer ratio. M is equal to V out divided by V in is equal to D. So the buck converter has a linearity, okay? Linear control of the output voltage. That is a characteristic of the buck converter. It's a linear control of the output voltage, right? And I'm going to add a condition to it as long as it is in a continuous conduction mode, okay? As long as it's in a continuous conduction mode, it has got a linearity, so you can actually say, you can predict that if this is my D, I basically have a linear function which is V out by V in. We will see some very interesting characteristics of the other converters as well. So the salient points is that D is always less than 1. You can't have D more than 1, right? And M is less than 1. And M is, in this particular condition, M is independent of the load current. There is no dependence on R out. There's no dependence on the load current, right? And you have a linear function with respect to D. V out is controllable with D. Because we use this in number of places. We use it in basically M is a transfer ratio, right? And the M we retain when we explain about discontinuous conduction mode, explain about buck boost, explain about.
M is actually V out by V in.
Yes.
It's not D.
Right. M is V. That is important clarity. M is V out by V. It's a transfer ratio. Yeah, it's a transfer ratio.
Okay, you are doing small signal analysis, so transfer input output transfer ratio will come into.
Yes. Yeah. Okay, so
because M is transfer function.
you want to write the transfer function?
Output voltage input voltage in small signal analysis. I don't remember correctly that you call it as transfer function.
No. That it's not called a transfer function. We normally have basically you have either V out by V in, which V in is the injected signal in the open
V
loop.
out by I in.
Right.
Remember like that. There is some terminology for that.
Yeah, we never use V out by V in. It's not the transfer function. It's not the transfer. So we will not be using MS. Yeah. All right. So we have. Now let's talk about discontinuous conduction mode. What happens in discontinuous conduction mode, right? Discontinuous conduction mode is that the inductor current goes to 0. Okay, the inductor current in a cycle goes to 0. So what we have shown here is, this is your IL, okay? IL starts from 0, that's point number 1. It starts from 0, right? So I value is 0. I value does not exist anymore. It goes to some I peak value, then it comes to 0. Now it can come to 0 anytime after, let's say, D, right? And then when it comes to 0, this is, we call it D3. So there's a D2 and there's a D3. So we divide the one time period for the inductor current in 3 parts, D, D2 and D3, okay? And but the principles apply because the voltage, average voltage across the inductor still has to be 0. So you can say, okay, VL, or say V, and what is the voltage here? It's V in minus V out, because this guy is on, so this is V in, this is V out. So V in minus V out multiplied by D, right? And then voltage here is minus V out you can say plus this voltage times D2 has to be 0. Right? That's your, and that's how we derive. This is the same equation, V in minus V out times D minus V out times D2 is equal to 0. Right? So we are, let's see, and then what we do, we have also got an I peak term here. Let me just make sure I got it right. So the average current here, I out. Okay, how do you calculate I out? You can calculate I out by calculating the area under this triangle, okay, plus the area under this triangle, dividing by the time period. That will give you I out. That's the average function, right? So that's what we do. We calculate, we say, okay, this here is dTSW times I peak divided by 2 is the area of this triangle, right here, okay? Because it's half times dTSW times I peak. So that gives you the area under this triangle. And this guy here gives the area on the right triangle. Then you just divide both of them by TSW to average it. That gives you I out. Okay. So with these two equations, you are able to calculate D2. Now, you're also able to calculate I peak simply by looking at it. You say, okay, I peak essentially.
Y is equal to mx.
Yeah, exactly. Exactly. So you have I peak here, and then your D2 term here, you stick this I peak into this term right here, and you try to solve for D2. Okay? And D2 so once you solve for D2 here using this equation, you actually can stick D2 back in here, all right? And the formula you get is right here. V out is equal to V in divided by, and you can simplify it if you introduce this term, inductance time constant, and so your transfer ratio now is defined by this function. It's highly nonlinear, as you can see. At least appears to be nonlinear, right? So it's a nonlinear. So if you were to plot the transfer, if you were to plot the transfer ratio, I'm going to erase this. If you plot the transfer ratio, you're looking at, this is your D, this is your M, right? So you had this for the continuous conduction mode, okay? Now in the discontinuous conduction mode, you are looking at, so if this is your 1, the discontinuous conduction mode, you're looking at waveforms which are going like this. And for this here, tau L is 0.001, and for this one, let's say it is could be tau L is 0.05, right? So you can also look at the m. If you look at the m function, 2 divided by square root of 1, sorry, the 1 plus square root of 1 plus 8 tau L divided by d squared, which is equal to 2 divided by 1 plus, you can also make this 1 plus, assuming this portion is small, 8 tau L divided by d squared, or half. So which is equal to 2 divided by 1 plus, now so you can kind of see the behavior here. 2 plus 4 tau L by d squared. So when tau L is very small, this almost approaches 1. Okay, so when tau L, so this is sort of a quick way to verify that the curves look okay. So when tau L has to be really, really small for this curve to hit 1. Okay, if tau L is bigger, then obviously this term is going to be less than 1. That's why you see the curves which move up and down because of the dependence on tau L. Okay. So, so what you have here now, and also if you look at M, now we have got all these terms. You know, we have R, L, right? PSW. So you have got these terms. Most important is you got R in there. That means M is now a function of the load current. M is now a function of the load current. And for a given duty cycle, M is larger for DCM than for a CCM operation. So if you draw a line here, and you say, okay, for a given duty cycle, I can have much larger transfer ratio if I operate in discontinuous conduction mode, right? But the disadvantage of discontinuous conduction mode is that you have much higher current levels inside that converter. You can have a lot of EMI issues, and but you get a little bigger bang for the buck. So that was the buck converter. Now, I think we'll take it from here and go into, okay, let's discuss the transition point. Now, what is the transition point between CCM and DCM? What is the transition point? Transition point is when D3 is 0, right? That means this period here is 0. D3 is 0. Okay? When D3 is 0, that is the transition point. And that transition point is defined by these equations, where you still have S on is V in minus V out by L, S off is this, and your I peak essentially is defined by this equation, V in minus V out dPSW by L. Easy to find out from the triangles. And this is your average current, right? V out by R is your average current, which is dV in by R. Because here you're still in a critical point, so you can use D to define V out. dV in, you use D, so you replace that. And then R critical falls out from these equations as such. And and L critical also follows from these equations. And what we have, the final values. Now, what is R critical? R critical and L critical. That means that if your load, if your load R load becomes more than R critical, then you're going to go into discontinuous conduction mode. And if your inductor you're designing, okay, goes less than L critical, then you're going to go into discontinuous conduction mode. So that's the buck converter in cycle by cycle switching time equations. Now, okay, we still have a few minutes. Now let's talk about small signal modeling. Right now, when you're dealing with switching times, it's very difficult to plot a Bode plot analytically. It's very difficult to actually in PSpice, if I'm using buck converter and I'm using cycle by cycle simulation, I cannot plot Bode plot. I cannot understand what is the transfer function, okay, with respect to. So unless you have a specialized equipment, when you make a power supply, unless you have specialized equipment, you could not really determine the transfer function. You have to build a prototype, and then only you could determine the transfer function. So. So what has happened is, over a period of last few years, several attempts have been made to develop what is called small signal model of the switching element we were talking about, which included the switch and the inductor. Okay, so I'm going to erase this, and I'm going to draw our switching element for the buck converter, which is basically this. Okay. Now, so the thought is that if you could replace the switching element with something which is non-switching but still has the same behavior pattern, just like we did in BLDC motor. And in BLDC motor, we took the whole inverter out and replaced them with continuous voltage sources. The same concept is here. Okay, how do we replace this switching element with something which can give us Bode plot? All we are interested in is getting that Bode plot, that transfer function, open loop transfer function, the power supply, so that we can actually compensate the whole power supply before we build it. Okay, before we go into expense of figuring out how to stabilize the power supply. So the first attempt which was made was in Caltech, and it was what is called trying to derive state variable equations for your converters. Okay. Now, I'm not going to go through the math for you. All I just want you to show how you can quickly derive the state variable equation. So, what was done? Let's look at this circuit again. Okay, and we look at its circuit where we're going to pay some attention to the inductor current and output voltage. Right, those are the two variables which are important to us. So if I rewrite the equation, di by dt is equal to dV in minus V output by L, because the voltage here is basically dV in, right? Because of the duty cycle of this switch here, dV in minus V output divided by L, okay? And dV by dt, which is the total current in these two branches, right, is I by C minus V output by RC. You can take the C out for a time being. C dV by dt you can see. C dV by dt is the current in this branch, right? So if I'm talking about the inductor current or the inductor current is sum of capacitor current plus a load current. So C dV by dt is equal to inductor current minus V output by R, which is our output load current, right? So I can write these two equations in this form. Di by dt is equal to minus 1 by LV0 plus dV in by L, right? That's pretty straightforward. With these two, and dV by dt is equal to 1 by Ci minus 1 by RCV output. Okay. Now, this derivation here, you can also write down in the classical state variable method, which essentially is, we have so the classical way to look at state variable equation is x dot is equal to A, okay, x plus B U, and then y okay, we can use Cx plus D. Now, you can also look at those equations in the matrix form, which says, all right, so x dot is Ax plus Bu, and if I were to just use x1 dot, x2 dot, and here you can say x1 dot, I should say dot. So my x1 dot